Now let's look at a solution for two-dimensional LP. The algorithm that we're going to cover for this problem is an incremental algorithm. This is very similar to the gram scan. So the gram scan was also an incremental algorithm. We were adding the points one by one, and we were maintaining a solution for all the points from 1 to I, right, if you remember that. We're going to do something very similar here. We're going to add the constraints one by one, and we're going to maintain a solution for all the constraints 1 to I. So let's do that. Let's assume that I have considered the constraints 1 to I minus 1, and they've given me this feasible region, and I know a vertex of the feasible region that is the solution with respect to only these constraints. The important thing here to note is that in the algorithm, I just know the objective function and the vertex v, right? I don't know about the shape of this feasible region, in particular because if I want to compute the entire feasible region, then that's essentially equivalent to a convex hull algorithm, so it needs n log n time, right? So therefore, I cannot compute the entire feasible region. I can only know about this vertex if I'm hoping to get a linear time algorithm. But anyway, so I have this point v in my algorithm. That's my assumption. So now let's add the constraint I plus 1. And if you're curious, the algorithm is actually very simple, but I'm going to explain what it means. So let's add constraint I plus 1. As we covered previously, the constraint is equivalent to a forbidden region or a forbidden half plane. If the constraint I, number I, forbids that part of the picture, crucially, it does not forbid the value v. So the value v was the minimum that I could have that could satisfy constraint I minus 1. And if it is still satisfies constraint I, then it's still the minimum, right? Because adding the constraint number I can only make this worse. It cannot make it better, right? I cannot find a more minimum number if I add another constraint. I can only forbid new stuff, okay? So therefore, if v was the answer before, and if v satisfies constraint I, it should be the answer again. And that's in line number 2.1. And if the constraint number I does not violate v, in other words, if it does not forbid v, then we don't need to do anything. Now, how do I know this? How do I know whether constraint number I violates v or not? Well, as I covered, I know the value of the v, right? I have the coordinates of the v. So I can just plug it in the constraint number I. If the inequality is satisfied, then I know that it does not forbid it. So therefore, I do nothing. So that's the easy case. So now let's look at the difficult case. The difficult case, if it forbids, so you add a new constraint and you realize that the answer that you had from before is now forbidden. The observation that we can make here is that if I look at the boundary of the constraint, like this line over here, then the new answer should be along this boundary. And again, I think I will have the time in the exercise class to prove this or to think about this, but let's just assume that this holds. In other words, the new answer is along this line. That is the main geometric algorithm or observation that helps us solve this. So how do we use this? Okay. So we are at the boundary of this constraint. What this means to be at the boundary is that this is an equality. If this is an equality, and assuming this guy is non-zero, then I could exactly work out what x2 is. Right? x2 equals this. And now here you can see that I colored x2 green because now x2 is not really an unknown. x2 depends entirely on x1. x2 is a function of x1. So therefore here I have only one unknown, I only have x1. If I know x1, x2 is uniquely determined. So therefore I can just replace x2 in all of the previous constraints, 1 up to I minus 1. And I've replaced x2 with this value. So if you replace x2 here, then all of these constraints have only one unknown, which is x1. So it can be solved using the previous one-dimensional linear program. And that describes line number 2.2. If the constraint violates V, then we solve the one-dimensional LP with constraint 1 up to I minus 1 on the boundary of constraint I. And that essentially means this operation that we did. Once you solve this constraint at the boundary of this, you get a value for x1. Then you can plug it into this equality and you get the value x2, and therefore you get the new answer v prime, and then you can repeat this algorithm to find the final answer. The analysis of this is actually not tricky at all, but unfortunately, in the worst case, this algorithm can run in n squared time. This is because solving one-dimensional LP takes linear time, and if we are unlucky and case 2.1 never happens, and for every iteration of the loop, this 2.2 runs, which takes linear time, then that's going to be n squared in total. So this algorithm, even though it's quite ingenious, it is very inefficient. It's worse than just computing the convex hull. If you want to use an n squared algorithm to find the bridge, then it's totally pointless.